In this video, we're going to talk about the management of waiting lines. I know that most of the things that are in Chapter 18 of the Stevenson Operations Management textbook are things that you've seen before, at least from being out in the, being out in public. However, I don't know that we ever sit down and really try to turn all of the things that we see out there into formulas. And so one thing that you will definitely notice in this chapter is there are a lot of formulas because there are a lot of different variables that we need to consider. Number one is the customer arrival rate. How frequently are your customers coming into a system? We also refer to the arrival rate oftentimes as a Poisson distribution. That's opposed to a normal distribution, where we have just as many coming in on the left side as we do on the right. Instead, a Poisson distribution is shifted usually more to the left. Another thing that we normally end up talking about is the average number of customers who are waiting for service, right? How many people are just there waiting, being backed up, or how many are actually being served? Number of servers, this is the number of different registers that are open that'll let you get through there. The service rate per server, the service time, which is the amount of time that is being used. Okay, this is the amount of time that each person is being served whenever they finally get through to it. Average number of customers being served, a utilization factor, very important to us as a vendor. If we're the ones who owns the bake shop, we need to be looking at, what kind of utilization do we have of our servers? Because we can speed things up by having more servers, but from the owner's perspective, there's a cost associated with that. Next one is the average time that each customer waits in line, and the average time that the customer waits inside of the entire bake shop, if you will. That's the amount of time that they're waiting in line and the time that they're being served. And then finally, what's the probability that you're going to have no customers in the system at all? All right, example 1, chapter 8, goes through and it talks about this bake shop. And in the bake shop, we have customers arriving at 18 per hour, 18 customers per hour. They're based on a Poisson distribution where the mean is 18. It also takes the average clerk 3 minutes per customer. Again, this is an exponential distribution with a mean of 3 minutes. So what we have been given is that our customer arrival rate, which is lambda, right, is 18 customers per hour, and our service time, which is 1 over mu, is 3 minutes. Now what you start needing to do is find what the variable is, determine the symbol that's associated with that variable, because there are equations that we can use to convert things that we know into the variables that we don't know. As a matter of fact, to get things started, what's the arrival rate? Arrival rate was given, that's 18 customers per hour. The next question is, what is the service rate? Well, we were given service time and not the service rate. And there's a difference here, okay? The service rate is represented by mu, and the service time is represented as 1 divided by mu. So what we need to do is we need to take and convert this, and once we convert it, we also need to make sure that all of our units are of the same measure. So this is talking about customers per hour, and this is in 3 minutes. So what I want to introduce you to here is a way of managing your equations. All right, first of all, we need to rearrange this equation here where 1 over mu equals to 3 minutes. So you remember from algebra, if you take the mu to this side, then 1 divided by 3 minutes is what mu will equal. So this is a way of managing your units. Mu, which is the service rate, equals 1 customer every 3 minutes. We need to convert this minutes, though, to hours. And so if we put 60 minutes up here and hour down here, right? So there's 60 minutes in an hour. The minutes and the minutes cancel out because we have minutes in the numerator, minutes in the denominator. So 1 times 60, 60 divided by 3 is 20 customers per hour. All right, let's continue on here. What's the average number of customers being served? This little r is, we calculate that by coming up here. We notice that the average number of customers being served, here's an equation for it. That is the service rate, the customer arrival rate divided by the service rate. We have already calculated, or we've been given lambda. We know mu. So 18 customers per hour divided by the mu, which is 20 customers per hour, gives us an R of 0.9. All right, so the average number of customers being served in this facility where there's only one server is 0.9. Average number of customers in the system. This is, again, I think that the equations can often throw you off. The equation says L sub S. And the sub S means, what's going on inside the system. All right? And so we have the average number of customers in the system, and then we have this L sub Q, and the L sub Q is the average number of customers just in a line. All right, so again, to find out the average number of customers in the system, L sub S, we need to first calculate the L sub Q because we've already calculated R. L sub Q again, number of customers in the line. We can come back up to our equations chart. And in the equations, we see that we can get that by taking lambda, squaring it, and then dividing it by mu times mu minus the lambda. All right, back down here. L sub Q is lambda squared. Lambda is 18 customers per hour. So I'm doing that twice, 18 customers per hour, 18 customers per hour. We're going to divide that by mu. See how we're dividing? We have 20 in the bottom, 20 customers per hour. And then we're also dividing it times mu minus lambda. Mu is 20, lambda is 18. We can see once again from unit analysis, this customers cancels out this customers, that cancels out this. Those cancel out each other, this cancels out each other. So once again, the number of customers that we're going to have in a line is going to be 8.1. We get that by dividing 18 times 18 divided by 20 and dividing by 2. All right, so now we can calculate the number of customers that are being served because L sub S equals 8.9 plus 0.9, so that's 9 customers. All right, the average time that a customer waits in line, we can now calculate this. That is WQ, and the reason for the Q there is we often refer to a line as a queue. So they use the sub Q. So WQ equals L sub Q divided by lambda. We've already calculated the L sub Q, which is 8.1 customers. We know lambda from before. So 8.1 customers divided by 18 customers per hour. Customers cancel out. 8.1 divided by 18 equals 0.45 hours. Again, this is the average amount of time that we could expect a customer to be waiting in line before they get up to the service counter. Now, the WS, the amount of time that they spend in the system, is the amount of time that they spent in line plus the amount of time that it takes to be served. So we've calculated WQ. We know the amount of time that it takes us before to be served and the number of customers that can be served per hour. So we have the 0.45 that we just calculated plus 1 divided by mu, 1 divided by mu, which is 20 customers per hour. This ends up being 0.05 plus 0.45. So the amount of time that a customer would expect to be inside the bake shop is half an hour. Now, from the bakery owner's standpoint, one of the things that they're concerned with is, what is our utilization factor? So the utilization factor is and it's this, P is what we end up using here, is lambda divided by the number of servers, in this case 1, times mu. So 18 customers per hour, lambda, divided by number of servers, here's 1, divided by mu, which is 20 customers per hour. So the utilization is 0.9, or 90% of the time, the one server is going to be busy. Now we could go ahead and we could increase the number of servers in there. And if we increase the number of servers and bump it up to 2 servers, what does that do to our utilization? Now we're going to have 18 customers per hour divided by 2, divided by mu. So we're only going to have 45% of the time that each one of these servers is actually being used, okay? So from an owner's perspective, we're going to have somebody to be paid to be just standing there for, 55% of the time, because 45% of the time they will be busy. So once again, what's the probability here that there are going to be no customers in the line? Now this is what we were just touching on. If we have a service rate of 0.9, that means 90% of the time the server is busy. So the time when there's going to be no customers in line is 1 minus that. So 10% of the time they would be idle, right? If we have 2 servers, 55% of the time they would be idle. Now what I want you to do is to think about from a baker's perspective. If a vendor comes in and says, we could put in a new system to speed up your checkout. And what will happen is that we will be able to drop your service time from 3 minutes down to 2 minutes, okay? Now that we've reduced the amount of time that customers are waiting, we expect that you're going to have fewer customers that come in the door and then say, I don't want to wait that long today, and they'll turn away, or they will get in line and that they'll stay in line. So what we expect is that we will jump from 18 customers per hour up to 25 customers per hour. So again, you're going to drop the service time, you're going to get an increase in the number of customers that you're serving, which means that your sales will go up. And what you're trying to determine here, is it worth it for you to be able to go ahead and put in this system? So what I want you to do is, based on these new numbers, calculate the following metrics, all right? We've already talked about them. They're already up here, but take a chance and go through here and see what happens whenever we change the service time and we change the number of customers that are coming in. Good luck.